Hi, what we're going to look at now is just a quick revision of what we've been going through. So we've been looking at a range of t-tests. We've had 3 flavors of t-tests. So a single sample t-test, a 2-sample t-test, and a paired t-test. And we've had a few examples of how to look at these. So the first example I had something about electricity consumption. We were looking at, in the broader context, how much electricity do Australians use relative to other countries. And we were particularly interested then in to say, well, what is electricity consumption in Western Australia relative to the national average? So we had some idea that there was a null that we wanted to compare to. In this case, it was the national average, and we wanted to say, well, is WA daily energy use equal to the national average, which is 16.5 kilowatts per hour? Our alternate hypothesis is that WA energy use is not equal to the national average. So we're just going to follow that same format, equal to something, not equal to something. To conduct our test, we set an alpha level, which is going to feed into our p-value decision rule. We conduct the test and then we try and say something meaningful. But of course, the first step in our process was to create a graph. So we could have gone for a histogram or a single sample in a horizontal box plot for this. Gone for the histogram. You can see here, we've got here, okay, there's the sample mean, 20.4. It's a bit higher than our hypothesis value of 16.5. And so what we're trying to understand is whether the difference between our observed sample mean of 20.4 and our null hypothesis value of 16.5 could be due just to sampling variation. So we conduct our t-test. We know how to conduct these in R. So we have our test here. So we specify the null hypothesis value, which in this case is 16.5. This is my data set. So with the data set, apply the t-test to the column WA1. And then we looked at our p-value, and our p-value is less than 0.05. So we reject the null that this sample is drawn from a population with mean 16.5. We know if we look down here that the sample mean is 20.4. So I told you that, but the t-test output will report that as well. And so because we know that, we can then say that, well, actually we know that they're different and the sample mean is higher. And then, we've conducted a test. For us, the important thing is then to be able to think about going on and saying something useful about what the differences might be. Are there any real policy differences? Is it environmental conditions? What are the reasons for those differences? The next example we talked about was coal, and it was, just a stylistic setup saying that some people have claimed that it would be a good thing to expand coal in Australia if it displaced less energy dense coal in other markets. Okay, I'm not making any statements about that. That's just a claim that's been put out there. So we wanted to test that. And we can see we start off, we've got 2 samples, an Australia sample and a China sample, looking at the energy density per kilogram of coal. And we can see that, the Australian sample looks both a little bit more spread out and it looks a little bit higher. So it does actually look a little bit more energy dense than the China coal for this example that I've set up. So we want to formalize our t-test, but we know that before we go on to our t-test, we're going to conduct a variance ratio test. So we're going to conduct this test so we know which formula to use. Should we use the equal variance t-test formula or the unequal variance t-test formula? So we set up this test. The variance of group 1 is the same as group 2. The variance is not the same in group 1 as it is in group 2 is our alternate hypothesis. Same sort of setup. We set the alpha at 0.05, conduct the test and apply the p-value decision rule. So if we know how to do that in R, you can see that I've got with my coal data, so that's the name of my data set, apply the variance ratio test, and the command for the variance ratio test in R is just bar.test, and these are my 2 samples. And really we're just looking at the p-value here, and we say that the p-value is less than 0.05, therefore we reject the null of equal variances, and we go on and implement the t-test with unequal variance. So we formalize our t-test. The mean for group 1 is the same as group 2. The China energy density is the same as the Australian coal energy density. The mean of group 1 is not the same as group 2. So I'm happy for you at this stage to just use generic group 1, group 2, but you might want to think about, taking some ownership of the problem and saying, well, it's the mean for the energy density in China is the same as the energy density for the coal in Australia, or something. You could think about framing these null and alternate hypotheses in terms of the language that makes sense for the context that we're working on. Rest of this is the same setup. We have an alpha of 0.05, which is going to come into our p-value test, and then we conduct the t-test. So here we are in R, we know, with the dataset coal.data, apply the t-test, the name of the two columns of data, which are Australia and China, variance is equal to false. And you can see here we get this very small p-value. So because we get this very small p-value, we would reject the null of equal means. And we have the mean of sample X and Y. So it doesn't pick up the names, but we know that X is the first sample, that's the Australia sample, Y is the second sample, so they match up here. So that's X and that's Y. So down here, the Australian sample, almost 690 kilojoules per kilogram, and the China sample, a bit over 6,550 kilojoules per kilogram. So in the way that was set up, that would say, yes, they're different, and yes, the coal per kilogram is more energy dense in Australia. Of course, there are all the complications of transporting this coal and all the other things that we would want to consider before we did anything, and saying that, we should actually try and displace other coal with this Australian coal, and these are stylistic values. I'm not saying that I've actually sampled all of these relevant coal ore bodies. Now, the final example we had was a paired t-test. So the context for looking at this was what happens when we have solar electricity installed. And one thing people worry about is, will people start using more energy if they put on these solar panels? Think, I'm free from the constraints of government, I'm just going to use more energy, and overall that might be a problem for us. So people worry about that. So we want to test that proposition. We have measurements on the individual houses before the PV is installed and after the PV is installed. So because we have these paired measurements, there's this structural dependence between the two observations, we can conduct a paired t-test. So we set up, as with all of these, we set up our plot. So for the paired t-test, we tend to go for the horizontal box plot, and we can actually see from our box plot that most of our middle 50% of the data is sitting pretty much straight over zero. So that's a sign, before we even conduct a formal test, that most of the observations are split right around zero, which would be an indication that there's been no change in behavior. There are some people that are using a little bit more, some people that are using a little bit less. They're just situated right around, clustered around zero. So for our paired t-test, we have this quirky null, which is an easy one, but allows me to distinguish what type of test you're doing. So the mean of the difference series, so it means that we subtract one observation from the other. Mean of the difference series is not equal to zero. So there are our two hypotheses that we need to set forward. All of the rest is pretty much the same. Set alpha at 0.05. We know that feeds back in terms of our decision rule. So because we've set alpha at 0.05 is why we have this p-value decision rule of 0.05. And then of course we want to say something useful. We don't ever want to really just be conducting tests for the sake of conducting tests. We always want to be able to say something useful. So then we implement our paired t-test, and we just put the setting on paired is equal to true. And when we implement the paired t-test, we see that the p-value is above 0.05, so that means that we do not reject the null. So the null was, there's no, the implication of the null is that there's no change in behavior once you install PVs in terms of the amount of energy that you consume. So that would be a good thing if people were worried about the potential for this rebound effect. When we introduced an energy saving device, do people just use more energy? We introduce lower fuel consumption cars, do people just drive more? So this rebound effect in terms of energy consumption is a broadly held concern in many markets. And that is an opportune time for a break.